Welcome to the course on the holistic smart energy system validation again. So as power and energy systems are becoming smarter, more decentralized and more dynamic, Module 3 is designed to introduce you to real-time simulation and hardware in the loop, equipping you with insights in advanced laboratory validation methods. This module consists of 3 parts, each designed to build your understanding step by step. The first part is about control hardware in the loop applicability and examples and will be provided by me, and I will introduce myself in the next slide. The second part is about the power hardware in the loop concept and will be delivered by Dr. Ziwang Feng from University of Strathclyde, who works as an research associate. And the last part will be about geographically distributed real-time simulation and will be delivered by Dr. Mazer Said, who is an assistant professor in University of Strathclyde. So again, my name is Alkistis Kontou, and I'm a PhD candidate in National Technical University of Athens in the School of Electrical and Computer Engineering. My research area is regarding advanced laboratory validation methods, and specifically in hardware in the loop methods, and also in control of smart grids and microgrids. And now we will discuss and we will go into the first part of this module about the control hardware and the loop applicability and example. The outline of this module is the following. So first we will discuss about conventional testing approaches versus hardware in the loop method, and we will see the advantages of hardware in the loop. Then we will give more details and how to implement control hardware in the loop, and we will proceed with some examples of control hardware in the loop applications on advanced testing of smart grid controllers and testing of smart protection schemes. We will conclude with some remarks. Power system validation has traditionally relied on 3 distinct approaches, each with its strengths and limitations. The first and the most common is simulations. Simulations rely on mathematical models to replicate the behavior of power system components and dynamics. However, the accuracy heavily depends on the fidelity of those models. Then is conventional hardware testing. This method involves direct testing of physical hardware, such as a photovoltaic inverter, under controlled predefined input profiles. A typical test setup includes a PV simulator, the inverter as hardware under test, and a grid simulator, and a power analyzer. While effective for functional testing, this approach often lacks dynamic interaction with broader system elements. And finally, laboratory experimental setups. These setups are generally tailored to validate specific functions or scenarios. While offering real-world testing environments, they tend to be limited in scope, focusing on particular aspects rather than holistic system behavior. And here comes hardware in the loop simulation. Based on this method, hardware equipment such as relays, controllers, motors, and PV inverters, etc., are incorporated into a simulated system. For this to be feasible, the simulated system must be computed in real time, as the device under test works in real time too. Digital real-time simulator has this capability, and it computes the simulation model in real time with a time step of 50 microseconds, and for power electronics it can go up to 1 to 3 microseconds. It also offers capabilities for input and output signals, digital, analog, or communication-based, etc. And some of the most famous simulators are produced by RTS, Polar-T, Typhoon, etc. The equipment can be tested repeatedly and economically under conditions as close as possible to the real operating conditions. Why to choose hardware in the loop validation method over the conventional methods? Here we will see a set of advantages, and they are not only limited to those that are mentioned here. So HIL enables testing of the hardware under test in conditions that closely resemble real-world environments, allowing for more accurate and reliable designs before field deployment. It also provides a controlled and a safe environment for the development and validation of new applications that significantly reduces the risks associated with physical testing. Then, the system under evaluation can interact with the real-time simulation of the power network. This uncovers weaknesses and operational issues early, just as they would appear in actual deployments. By enabling early detection of issues and streamlining testing processes, hardware-in-the-loop accelerates the development cycle and time to market for new products. There are three main types of real-time simulation, let's say. First is the control hardware-in-the-loop, where a control unit, for example, an inverter controller, a digital relay, an energy management system, is interfaced with a real-time simulator. The second type is the power hardware-in-the-loop, where a power equipment now is interfaced with a real simulator, like a PV inverter, a battery energy storage system, a generator, and an amplifier is required for this interconnection. And the third one is a geographically distributed real-time simulation, where we have a connection of two remote systems. It can be either two remote simulators, real-time simulators, or it can be a real-time simulator and control devices, or real-time simulator and power devices, or combinations of them. Now that we introduced the hardware-in-the-loop method, let's also discuss a validation chains for rigorous step-by-step testing. Distribution networks are evolving rapidly. They're becoming smarter, but also more complex, with the integration of power electronics, advanced ICT, smart meters, and more. To manage these modern grids effectively, we need advanced control strategies. And importantly, these strategies must be rigorously tested before real-world deployment. To address this, a structured testing chain has been developed, one that evaluates control algorithms step by step through increasing levels of realism. We start with pure software simulation. Here, both the power system and the control logic are simulated, typically using platforms available like MATLAB or Simulink or other available platforms for EMT and RMS studies. This is useful for initial testing but lacks real interaction between power and control domains. The next level is the software in the loop, as we can see in this part of the testing chain. In this setup, the power system and the control system run on separate software environments, exchanging data in real time. This co-simulation gives us better insights into control performance interactions, even though everything is still virtual. The next phase is about control hardware in the loop. This is a big leap forward. The power system is simulated in real time using a DRTS, while the control algorithm runs on an actual hardware. This lets us test realistic timing, data handling, and system responses, uncovering hidden weaknesses like delays and noise sensitivity. However, control hardware in the loop alone doesn't capture how the controller interacts with the real devices, physical devices. And then that's where we come with the final phase before actual field deployment. The final stage combines control hardware in the loop and power hardware in the loop. Now, the digital real-time simulator interfaces not only with the controller hardware, but also with real power components like inverters, motors, and generators. This hybrid setup offers the closest laboratory approximation to real-world operation, enabling validation of the control system's functionality, hardware integration, and performance on a realistic but safe platform. The rest of the presentation will focus on control hardware in the loop method. As we have already discussed, this method concerns the interfacing with the real-time simulation of inverter controller, digital relays, central controllers, etc. In order to perform control hardware in the loop experiments, signals need to be exchanged between the real-time simulator and the hardware in the test. The signals used for the communication might vary depending on the application. So for the interfacing, analog signals, digital signals, or communication protocols can be utilized. For that purpose, usually peripheral cards are used. Time delays and noise introduced due to the wiring, digital to analog conversion, and processing capability of the device, etc., making the setup and the testing of the controller more realistic. Now we will see an example of inverter testing and we'll compare the simulation results for a pure simulation versus control hardware in the loop setup. So we noticed that pure simulation cannot always model accurately real conditions, for example, exact noise and time delays. So while we can observe a stable control in Simulink, for example, it can be unstable when we implement the same control in control hardware in the loop or hardware setup due to time delays, noise, real hardware implementation, etc. Here is the example where inverter's control filter is designed with specific bandwidth in simulation, and we observed instability in control hardware in the loop due to time delays for that bandwidth. So by performing control hardware in the loop, we can implement recalculation of the bandwidth to make the controller stable for the specific real-world delays. So control hardware in the loop allowed for tuning of the hardware in realistic conditions and in a safe environment. The next example is about hardware in the loop testing of industrial controller according to the grid code requirements in Greek system. Distributed generators must abide by network code of EU requirements for generators. Here we have an example of a utility-scale PV power plant and a central controller that manages the control requirements at the point of common coupling. The network code lays down the requirements for grid connection of power generating facilities. For example, the reactive power control at point of common coupling, the power limit control, and the frequency regulation, and others. So we will see the results of the testing of this industrial PV controller and the response that it should provide. This is the testing that was done for testing the controller in limited frequency sensitivity mode for overfrequency. According to EU code, the power plant under consideration shall be capable of activating the provision of active power frequency response. So the frequency threshold is 50.2 Hz, and the droop is adjustable between 2 to 12% with 5% default value. So the power controller should reduce the active power provision of the power plant with a delay less than 2 seconds and should prevail over any other active power set points. The next example is the investigation of the interaction of inverter prototype controller with eye-landing detection protection. A hardware in the loop testbed has been used to evaluate the behavior of different control techniques of the battery energy storage inverter controller and its interaction with the loss of mains protection devices. The hardware controller obtains voltage and current measurements, performs different control functions like the provision of frequency containment reserve, synthetic inertia, and inner control inverter controls, and produces the modulating signals that drive a detailed model of the battery inverter in the DRTS. The digital real-time simulator also models in detail the rest of an islanded system: diesel generators, loads, lines, PV, and a wind turbine. In addition, the voltage at the connection point of the distributed generators, for example PVs, is extracted by the DRTS and fed to an industrial relay that operates under loss of mains protection functionalities to test their interactions. The loss of main relay provides a digital signal that drives a breaker in the DRTS that connects the distributed generator in the simulated islanded system. A scenario of high renewable energy source penetration was simulated in the DRTS, where the wind turbine disconnection at its maximum production, 2 MW, was performed. The battery energy storage system was absorbing 0.5 MW, and the diesel generator was operating at its technical minimum, 0.4 MW, supplying a demand of 1.9 MW. The hardware battery energy storage system controller in the first case had only a frequency containment reserve component, and in the second, it also included synthetic inertia. The frequency transient under both control techniques is presented in the figure on the left. The frequency nadir in both cases does not exceed the settings of the load setting relays in the islanded system, which is 48.5 Hz. The main difference, however, between the two control structures lies in the interaction with the loss of mains relays. In the second figure on the right, the rate of change of frequency and the vector shifting angle transients are compared in both cases. The battery energy storage system operates only with the frequency containment reserve function, resulted in high rate of change of frequency and vector shifting angle transients that surpass the loss of main protection thresholds, leading to their tripping. As we can see in the figure, almost immediately after the wind turbine disconnection, the industrial loss of main relay trips, disconnecting the PV plant. Including synthetic inertia on the battery energy source controller, avoids the activation of the loss of main relay for the same event. The next example is about the testing of an adaptive protection scheme. This hardware-in-the-loop testbed was designed to evaluate the protection device's coordination in an adaptive protection scheme to deal with short-circuit faults. Prior to the actual implementation of the experiment, simulations of various faults have taken place for various system states to calculate the short-circuit currents. According to the observed results, the characteristics of different setting groups have been determined based on the solution of an offline optimization problem, and the different island states were grouped to 4 conditions. A real-time central controller is used to update the active setting groups of the relays based on the changes of the network topology. This central controller obtained the statuses of the generating units through DNP3 communication protocol, and then, according to its implemented logic, enables the relay's setting groups through ICCS-NTUA goose messages. Actual hardware relays were used, as shown in figure. The relays obtained their respective voltage and current measurements through analog signals as outputs from the DRTS. If their overcurrent functionalities detect a fault in the system, a digital contact drives the simulated breaker in the DRTS. The setting group's enabling condition is dictated by the status of operating units as presented in Table 1. Having the adaptive protection scheme enabled, several faults were performed, and the experimental fault detection times were compared to the theoretical ones calculated by the optimization problem. The comparison of the times is presented in the figure on the left. The figure on the right shows the simulated fault, its detection and clearance by the industrial relays. As observed from the figure on the left, the theoretical results and the experimental results present slight differences. One of the main observations is that during the subtransient state, so when we are less than 0.08 seconds, the diesel generator provides higher currents that result in faster fault detection time. Concluding today's presentation, hardware-in-the-loop testing provides an efficient and low-risk method for laboratory validation. It can be applied to both low power through control hardware-in-the-loop and high power equipment through power hardware-in-the-loop method. A state-state testing chain can be followed to progressively validate the system, and based on the results, refine and improve key aspects of the design can be implemented. Regarding control hardware-in-the-loop, it enables precise tuning of the hardware controllers in realistic and safe conditions, and control hardware-in-the-loop provides an effective platform for the rigorous testing of advanced control and protection schemes. Thank you very much for your attention. So please feel free to contact me on my email, and if you have any questions on this course or anything else, please do not hesitate to contact me. The part 2 of the module on real-time simulation and hardware-in-the-loop validation of modern energy systems is about the power hardware-in-the-loop concept and will be presented, as we said at the beginning of this course, by Dr. Zhingwang Feng from University of Strathclyde.